Professor Lev Filippov é professor da École Nationale Supérieure de Géologie e membro do Laboratório de GeoRessources. Foi homenageado e distinguido pela República Francesa ao ser agraciado com a Medalha da Ordem Nacional do Mérito. Este prestigioso reconhecimento destaca seu excepcional comprometimento acadêmico, dedicação e conquistas impressionantes. Welcome, Professor.
Let's start this presentation by present the place from where we are from. Map of France, Paris, you see Paris here, Strasbourg, two well-known city in France, and Nancy is just in between. Nancy, the university city, regrouping University of Lorraine, regroups more than 60,000 students with the high number of PhD students, 60 research laboratory. Nancy is very rich in engineering sciences, and one of laboratory in this area is the GeoRessources laboratory, with about 200 people, with more than 100 permanent researcher, technician, and administrative staff, 85 PhD students. But particularly, specificity of our laboratory is the existence of pilot pond. This is actual pilot pond, which about in 1960, renewed in 2007 with 2,000 square meter of surface devoted to process, to develop the mineral processing and hydrometeorology project with more than 150 the equipment available from small lab scale to big pilot scale. We have all equipment, and the work, our laboratory was working on the phosphate ore since several years, maybe several decades. And today I will present the recent advances we achieved in calcium mineral separation. You know that the main route to process calcium mineral containing ore is a flotation, but the fatty acid is used as main collector, but this process, this route is not easy to implement because of similarity of the surface property of main calcium minerals. Today I will focus, I will present how we advanced to separate calcium mineral on two type of sample. First sample is scheelite skarn, and the second sample is phosphate ore. And at the end of this presentation, I will focus how we performed the apatite calcite separation in acidic medium to perform the reverse flotation. Let's start by the consideration, some theoretical consideration. In the literature, we identified four parameters, four factors which influence the calcium mineral separation, flotation. Dissolution rate of mineral, that means solubility, surface mineral species, that means surface speciation, and we identified recently that the calcium site density on mineral surfaces drives the selectivity of separation. And finally, all these three parameters impact the mineral global surface charge, such as zeta potential, which control the mineral separation. sorry. If we start with the solubility, we can correlate the floatability and solubility. For example, it is easy to explain why gypsum, for example, apatite float not very well, while the gypsum and fluorite float good. But this cannot explain why the mineral with close solubility float differently. Let's introduce the calcium site density on the cleavage plane, because during the grinding you liberate, of course, the mineral grain, but export surface is maybe different. And knowing the distance between calcium ions on the cleavage plane, or explaining it as calcium site density, we can predict the collector absorption, because the different functional group will act differently depending on the calcium distance on the cleavage plane. If we consider this factor, what we see that the apatite is less floatable, while fluorite is the best floatable, the better floatable minerals. And if we compare this with the calcium site density, this corroborates very well. Based on this approach, we can develop some collector, new collector, or go to collector blends. Main species presented on calcium mineral surface depend on different other factors. And we can see that even calcite, the surface specimen of calcite is not only presenting as usual with calcium ion on the double electric layer. We can have the carbonate, calcium hydrogen carbonate, calcium hydroxide on surface. Depending on this speciation, absorption of collector will be different. Most interesting to see what happens on the apatite surface. In red, you see the domination of series of anion and cations present on the apatite surface. And depending on the pH value, one of these species may dominate. And this will define the collector absorption and consequently the flotation. For example, for pH below 4.5 in fluorapatite is presented on the surface by fluoride. In this case, it's floatability, not calcium phosphate, which controls the absorption, but the fluoride. And the global surface property of calcium mineral is depending on its origin. This is a most important things when we try to extrapolate data obtained at lab to industrial scale. We have to know something more than only chemical formula of minerals. For example, first diagram present well-known the zeta potential presented by Thomas Sundaran 40 years ago. We have a nice zeta potential curve for apatite and calcite. Big difference. We can choose the pH area where a collector as fatty acid will absorb preferentially on calcite surface, for example. But when you see the data on right, first line on right, for apatite from the same deposit, but the different zone of deposit. Same apatite doesn't present the similar surface property. This change depending also on the zonation. We also worked with the carbonate apatite from Brazil, and in the first diagram in the second row show the zeta potential or EIP of apatite. This is not close to 5, 6, this is below 3. We don't know, this does not exist. By changing the electrolyte, we identify that this is close, this is between 2 is 3. This means the zeta potential of apatite is depending also the EIP of apatite depending on the origin. And the last diagram shows a cloud of point. This is all data available in the literature about the zeta potential of calcite. You see, there is no one point. There is no one area of pH. This cloud of points. Yeah, this means that the most important conclusion: origin of minerals is crucial to develop something in flotation of calcium minerals, and specifically for phosphate ore. Now just let me go to the demonstration. We will start by the scheelite ore, skarn. Collector is fatty acid, thiol fatty acid. We tested different ratio between oleic and linoleic. For this study, I present only one ratio, 1.38 between oleate and linoleate. We used also other collector. As the present, we still with the sodium silicate, but combined with sodium carbonate. Comes from northern Portugal, this Tabasso skarn deposit, not exploited yet, this potential deposit. But what we see, 95% of minerals, they are calcium minerals. While we are looking to recover scheelite, is present only as 1% of ore. Okay, 95% is calcium, other calcium mineral. This is a challenge to perform the separation. We started with using fatty acid. First diagram shows the behavior recovery of 4 minerals: scheelite present by 3 oxide of tungsten, fluorite as F, apatite as PTO5, and quartz as SiO2. What we see that using the depressant, increasing sodium silicate, we can depress the floatability apatite calcite, while scheelite and fluorite have parallel behavior for recovery and for grade. This is not possible separate fluorite and scheelite. This corroborates very well calcium density on cleavage plane. This is very close for scheelite and fluorite. And the idea was to use the carbonation before flotation. How perform carbonation? Idea was to, based on the literature data, we choose the sodium carbonate. We treated our minerals with the sodium carbonate, and after added sodium silicate. What happens? Sodium carbonate, sodium silicate absorption is inhibited on the pure fluoride surface because of repulsion between 2 silicate anions. The distance between calcium is very, very small, and 2 silicate anions cannot absorb on the 2 calcium ions on the fluoride surface. But when we perform the calcination, this means the carbonation, we add sodium carbonate, we form calcite on the fluoride surface. And thus, on the calcite surface, density is low, distance is higher, and we can adsorb 2 silicate anions. This was very interesting, and we tested. You see that we increased grade from 6.63 to 1190. This is 2 times, and increasing also recovery. This effect was very significant because we increased at the same time grade and recovery. This works, this approach. And after we performed some density functional theory calculation, this quantum calculation, to see the absorption energy. This is bar surface of fluoride. When we add the sodium silicate, energy is around minus 100 kilojoule per mole. Then on the carbonated surface, energy is 2 times less. This means that we thermodynamically promote the absorption of sodium silicate when we treat before the fluoride by sodium carbonate. Preliminary treatment by sodium carbonate enhance the absorption of sodium silicate. Similarly, if at the concentration range, sodium silicate is presented by dimer, and here again we have some adsorption. This is adsorption happens, but it's low. But when we perform the carbonation, this increases the adsorption. We identified also another mechanism where the depolymerization of the sodium silicate is also favored by presence of sodium carbonate. This was theoretical, this contribution from quantum chemistry calculation. This was not observed experimentally. This was predicted, and we just tried to understand and confirm by using surface sensitive techniques such as infrared spectroscopy. And you can see here the black line is fluoride, red line is fluoride plus sodium carbonate. We observe very clearly the apparition of the sodium of carbonate peak at 1439. After, when we treat with sodium fluoride with sodium silicate only, we observe small peak of the calcium silicate at 1510. But this peak enhanced and doubled when we treat the fluoride with sodium carbonate at only after the sodium silicate. We observe that one peak of carbonate is switched, and we observe the formation of narcolite. This is the mineral, and this proves the proton transfer from sodium carbonate to the system to perform the depolymerization. Similarly, the XPS study allowed to identify this mechanism, that the presence of sodium carbonate because of the proton transfer promote the formation of monomer of sodium silicate, which adsorb efficiently on the mineral surfaces. Thus, based on this study, we choose the sodium silicate, sodium carbonate system as the present. We will try to now improve the collector efficiency. And we based on the collector-molecule interaction. When two collectors are very close, we observe the repulsion because of similarly charged heat group of collector. If you use fatty acid, it's carboxylate charged negatively. If they are very close, we have a repulsion. It showed it in on the diagram bottom of this slide. When distance is very large, there is no interaction. In the between of this point, we have interaction between the collector's chain. This means the hydrocarbon chain act, this gives the lower interaction energy. This means that thermodynamically we will promote chain-chain interaction. But when we use the sodium oleate and linoleate, the repulsion does not allow have interaction between the chain. And idea was to introduce in this the system saturated fatty acid with a linear chain and promote its absorption at molecular form. When we did this one, what we obtained, we can increase the absorption density of the collector on the mineral surfaces, increasing the hydrophobicity. And when we perform now the flotation test with a new collector, this all blue line are a new collector. In the diagram, recovery grade diagrams, we see that introducing the saturated acid or mixing the collector, blending the collector, improves the collector performance and allows to obtain 24%, 26% of concentrate instead of 11 before, by combining the only depressor and fatty acid. This is a conclusion for this first part of my presentation. We can perform selective flotation of shale from apatite and calcite, but selectivity is not very good compared to fluoride. And we can improve the selectivity by changing the collector formulation and controlling the ratio between the insaturated acid and saturated carboxylic acid in the molecule. Okay, now let's go. Can we extrapolate this data to the phosphate system, apatite, calcite, dolomite? We consider now 3 minerals. We keep all time the depressant because for example, reverse flotation, sodium silicate, sodium carbonate gives a very good result by depressing apatite floatability. Okay, but when we use only sodium oleate, for example, you can see that there is no difference in the floatability of 3 minerals. Very small difference, but cannot be explored at the industrial scale. While for phosphate ore, we have to reach more than 30% of PTO5, control the ratio between the calcium oxide and the PTO5, and otherwise we have to control the dolomite floatability to have less than 1% of magnesium oxide in the concentrate. What is, we focus now in collector blending, but using the collector with different molecular structure by blending the main collector with non-ionic reagents. Yeah, in our previous work, we already showed using aliphatic alcohol that improving absorption of main collector may be obtained as a result of molecular scale interaction at the mineral water interface. And this blending may enhance the flotation recovery and selectivity as a cumulative macro effect. And we attributed this improvement to the reduction of electrostatic repulsion between two charged collector molecules. Let's now see how this model may be visualized. Model 1, we have fluoride surface, oleate as collector, distance between heat group, depending on the distance of calcium on fluoride surface is 3.4 angstrom. Each calcium, we consider that each calcium ion coordinates carboxylate group oxygen. This means that each calcium absorbs one collector molecule. Schematic is as follows. This means that we have the molecule very closely adsorbed on the mineral surfaces. But in this case, this doesn't work because the distance is very short and repulsion dominate the adsorption. And model 2, same consideration in which we consider that only one of two calcium ions coordinate one carboxylate group works very well. This means that we observe the absorption of oleate on the mineral surface with no repulsion because distance is 2 times higher, but this gives low hydrophobicity. Okay, adsorption model works, but flotation results are not very good because of low hydrophobicity and because of the existence of water area on the mineral surfaces. We still with model 2, and we introduce the alcohol molecule. Alcohol is polar but non-charged molecule. This polar molecule, but there is no charge. Charge is neutral. In this case, we can introduce alcohol between two molecules with no repulsion. And because of the chain-chain interaction, adsorption layer may be stabilized. Similarly, this alcohol molecule can form ion molecular complex in the solution and adsorb on the mineral surfaces. Both two mechanisms lead to the more packed adsorption layer, higher hydrophobicity. This means they're blending the main collector with non-ionic reagents, and by controlling the chain-chain interaction, we can increase the absorption density, increase the hydrophobicity. The result I present in this slide, we obtained it on a calcite apatite dolomite system using the oleate as a collector and mixing it with ethoxylated alcohols. At 2 pH, pH 4.5 and pH 9.5. We know very well that at pH 9.5, fatty acid adsorb on the apatite surface. And what we observe at pH 9.5, that introducing the alcohol improve the floatability of all minerals. Apatite, calcite, dolomite, all minerals with no selectivity. There is one important conclusion that even the adsorption of non-ionic reagents are controlled by weak interaction, this chain-chain interaction. The selectivity of the primary corrector is crucial. This means to have synergistic effect, we have to have the difference in hydrophobicity. Even this difference is small. If this difference does not exist, there is no selectivity. If this difference exists, we can enhance the selectivity. And what is showed on the left diagram at pH 4.5, we increase the floatability of calcite and dolomite while apatite still depressed. I will show later why this happens at this pH, but the selectivity of Moin collector is one of factors we have to take into account when using these approaches. After two diagrams which show the infrared spectroscopy showed the enhanced absorption with the non-ionic reagents, we calculated the peak area, and this is the direct relation with the adsorptive quantity, and we showed that the absorption of the organic molecule increased when we use the mixture. But what is interesting, we showed that this absorption, this increase is depending on the molecule, linoleate or oleate. You know that the linoleate already in 1994 by Brandau was demonstrated that the linoleate absorb better, float better the apatite than oleate. Okay, what we observe here for increase of the absorption when we use linoleate is more significant. This means the selectivity and force of the primary collector also drive the synergistic effect we observe. If I simplify, more selective and more strong is a primary collector, more synergetic effect appears. It means more strong is synergetic effects. Okay. This was my first point and last point. How now extrapolate to the actual system for phosphate or flotation. And here I present the result we obtained by optimizing and understanding the depressant action of the phosphoric acid in reverse flotation using in situ Raman spectrophotometry. This means this is technique non-destructive. And we don't dry sample, we monitor the collector of phosphoric acid adsorption or interaction with mineral surface in situ, directly in the solution in the pulp, in flotation cell. We did also this one is a flotation cell. What we observed, the phosphoric acid acts with the calcite, of course, and with fluorapatite. But this is depending on the phosphoric acid concentration. On the left diagram, you can observe that on the calcite surface, the peak of new calcium phosphate phases appears at concentration 0.1 molar. This is first thing. For fluorapatite, this concentration is slightly lower. But most interesting thing is when we monitor the contact time, this is conditioning time, while on the fluorapatite surface, the new phosphate phase appears immediately when we add phosphoric acid. On calcite surface, this takes several minutes, 3 minutes, for example. This is first thing. New calcium phosphate phases appears on both two mineral surfaces. But if we are working in strong acidic condition, strong concentration, the new phosphate phases are delayed on the calcite surface for 2, 3, 4 minutes. Yeah. And second thing, for lower concentration of phosphoric acid, there is no calcium phosphate on the calcite surface. What means the formation of the calcium phases? This means the new calcium phosphate of calcium. This means that we passivate the mineral surface and we avoid the collector adsorption. This phenomenon is cyclic phenomenon. In the practice, sometimes when I discuss with some practitioners, they said, okay, you know, this works sometimes, this doesn't work sometimes. But to work, you have to control very well the surface state. If you, for example, perform long conditioning, in this case, you destroy these phases, we reform these phases, because this cyclic phenomenon. You see it increase after there is no phosphate, after this reappear, etc. This is depending on the conditioning time. And this interval is 15 minutes. This means in 15 minutes you can perform flotation, depress, and refloat. Okay, this conditioning time, this most important things, and also pH control is important. At the beginning, you see that for 3 minutes we have calcium phosphate and fluorapatite, and no calcite on the no phosphate on the calcite surfaces. When we analyze the proton consumption, we see clearly that a decrease in the proton consumption means surface passivation. If we passivate surface, there is no proton consumption, surface is passivated, and we can avoid also collector adsorption. And based on this result, we tried to confirm by flotation. On left, our theoretical, experimental, the confirmation of theoretical assumption. On the middle, we have the flotation of apatited calcite. When we fix pH, as usually, we fix the pH at the beginning. After we the pH drifted. We don't control the pH. In this case, you see, we can observe some contrast of separation. But this separation contrast is on the middle at a very narrow pH range. It is difficult to control this pH range between 4.5 and 4.8. While on the right we have the diagram in which we control continuously. We add phosphoric acid, but we start with low dosage, and we adjust the pH, we stop addition. And we add continuously the phosphoric acid. In this case, you have contrast in very large pH range. This is more easy to perform the flotation for second case with control of the pH. This confirms the hypothesis on the kinetics of phosphoric acid interaction with mineral surfaces. A similar data we obtained it on the magnesite dolomite system when we performed reverse flotation of dolomite and we depressed the magnesite. If someone works on magnesite ore, this approach may be also applied for dolomite magnesite separation. Okay, what a conclusion. This work reveals that the surface of fluoride conversion to calcite started from this minus 3 molar of the phosphoric acid and comprised between pH 2.2 pH 3. In this case, you have no selective flotation. To have selective flotation, you have to form bruchite. This is calcium or decalcium phosphate on the mineral surface to passivate the apatite surface and avoid the collector adsorption. Cyclic trends on brushwood formation have to be taken into account because this defines the conditioning time in actual flotation system. Best separation contrast was obtained between for the concentration between 10 minus 2 minus 3 more of phosphoric acid when the dosage were other distributed. And all these results were obtained using in situ Raman spectroscopy, which is a powerful tool to investigate the calcium carbonate, sulfate, and phosphate system. Okay, thank you very much for your attention.
Thanks, Professor. Uma pergunta, gente? Uma questão? Professor?
Great research and nice presentation. I have a question. Did you ever try the phosphate ore from Saudi Arabia? They have phosphate ore from Saudi Arabia. They have high calcite phosphate ore. It's a problem. Many reagent companies tried, research organizations tried, but they continue to have this recovery problem.
Yeah. Tomorrow I will present the result from tomorrow we have a presentation for the actual phosphate ore using this approach, but recovery issues is depending also on the collector. With the recovery issues for carbonated ore, this is one of problem, yes. But changing the here I present only result one stage. The surface control and separation on the pure mineral system. In actual ore system, you can play with the flow sheet. Yeah, combining the different flow sheet, you can solve the problem, recovery problem.
Mais uma, gente, para a gente encerrar. Mais alguém?
Okay.
No. Thanks, Professor. Good work on your presentation. Take this as a talk of our presentation.